sleep is one thing I didn't get to have too much. I was teaching yesterday until 5 p.m., so I had to take a late flight. So I hope you'll forgive me if it's not as well put together as my talks usually are. So I like this little graphic, which took me a surprisingly long time to make. Who in this room recognizes this curve? Okay. Everybody who works on climate should know this curve. These are the world-famous ice ages, as captured in the Epicadome Sea ice core. So basically, this is an Antarctic record. And what I'm going to try to convince you of is that to really usher in the future of climate science, we have to look fairly deep into the past. Because if we are going to understand climate on timescales that are relevant for adaptation, for instance, then we need the only reliable source of information that we have comes from the paleoclimate record. Obviously, that doesn't mean we're going to have to ignore everything else. I'm going to argue for a unified approach to the field. So this is the first point I'll make. There's really no climate without paleoclimate. I'll also make the case that climate informatics should be, in the words of Fagmus and Kumar, a case of theory-guided data science. Climate science is a graveyard for pure machine learning approaches that completely ignore the physics or the dynamics of the system. But they are ways, and I'm sure you guys have seen that yesterday, and you'll see more of that today, they are ways to really fuse the theory and the machine learning. I also make the case, this is what I've been spending a lot of my time over the past few years. It's not terribly glamorous, but standardizing data in paleo is something that was long overdue, and I think we're now at the point where we can start applying more systematic tools to these data sets now that they've been standardized. Something that would not have been possible 5 or 10 years ago, because basically every single data set was its own beast, and you needed to tailor code to every data set, which is obviously a nightmare nobody wants to deal with. And so I'll try to leave some room for discussion at the end about where the climate informatics community can explore and contribute to this problem. Okay, I'll start with perhaps the biggest success in atmospheric science, which is numerical weather prediction. There was this review in 2015 by Bauer et al. That was entitled The Quiet Revolution of Numerical Weather Prediction. And it argued that, as you can see on this graph, the skill of numerical weather prediction has consistently improved over decades. And this is only looking at the past 3 decades or so. And so here you have 3-day weather prediction, 5 days, 7 days, 10 days. And you can see that before the late 90s, 10 days was absolutely inconceivable, or you wouldn't even put on the graph. And now we're at the point where basically we were with 3-day weather prediction, 7-day weather prediction in the 80s. So we're slowly creeping up. And the difference between these two curves is the difference between northern hemisphere and southern hemisphere. And you see that that gap has been narrowing over time, and it's actually practically disappeared in at the turn of the millennium, which is attributed to the assimilation of a lot more satellite data from the southern hemisphere. Now, there's a lot of reasons for this success. And by the way, as you probably know, weather prediction is one of the aspects of atmospheric science that has the most direct impact on millions of people and on many aspects of economic activity. So there are very tangible benefits from that. Now, it's been a quiet revolution because it hasn't really gone up with a bang. It's been a fairly steady increase, or sometimes there've been losses, honestly, along the way. But looking at the long trajectory, we see that there've been consistent gains. And sure enough, this is because our understanding of the atmosphere has improved, and we have better models to show it. There's also more and better data to feed to these models for the initialization. There's improved data assimilation techniques. But I would argue that the most important thing that numerical weather prediction has for it compared to climate is that it's just had way more degrees of freedom. We do this every single day, and we do this with large ensembles every single day. So there's a lot of opportunity for learning. a lot of opportunity for models to fail and then be exposed to data, be improved, and for the trajectories to be corrected. That isn't the case so much for climate. So if you look at climate prediction, and here I'm going to use a fairly partial example of decadal hindcasts. So basically looking at predictions a decade ahead at various points that you can see on this map. So, you know, in the 1960s, 1970s, and you initialize your model, you let it run for 10 years with 3 ensembles, and this was just one of 4 models, I think, that was used in this particular paper by Emma Suckling and Lenny Smith. And what they basically argued in that paper is that these state-of-the-art climate models were hard-pressed to do better than a very simple linear inverse model, you know, very simple linear, empirical model. And so you wonder really what is, you know, all the hours of supercomputing time and all the fancy physics for if it can even beat basically linear regression. And arguably, you know, it's because climate is not really playing in the same arena as weather. Now, that doesn't mean we can't eventually get there. But one of the things that we really need is more degrees of freedom. And with a limited instrumental record, we just don't have as many decades to play with as we have days or hours for numerical weather prediction. We also could use larger ensembles. And similarly, we can use data assimilation. So I'm going to try to make the case that the last millennium reanalysis provides such a framework. It's a project I've been lucky to work on for the past few years. So basically, we can't really get out of this with the instrumental record, so we have to look at the paleoclimate record. There's other reasons why we might be interested in paleo. So this little blue curve right here, those are the same ice age cycles that you saw on my opening slides. They're on the time scale here is logarithmic, which is why they're a little stretched towards the present. But this particular graph shows you not the climate, but what we would consider the forcing of the climate. So this is the radiative forcing due to CO2, reconstructed from various sources over geologic time. And so what we have here are various scenarios for how this concentration is going to increase over the next century or so. And it's important to put that in the context of the geologic past. Now, as you've probably heard, current concentrations of CO2, which are on the order of 400 parts per million, haven't been seen in probably over 1 million years, and probably much more than that. In fact, to get anywhere close to where we think we'll be by the end of the century, you have to go back at least 100 million years in Earth history. So that means we're pretty much going into not unknown territory, but territory that we haven't visited in a very long time, that the Earth hasn't visited. And certainly, if you're familiar with climate modeling, this is not territory that climate models are designed to handle. Climate models are typically tuned to reproduce the climatology or the variability of, you know, a very small subset of the 20th century. So if we really, you know, we're asking them to predict climate a century into the future in these extreme conditions, but we really haven't given them the opportunity to learn from past conditions that are in any way comparable. And so that's why we need paleo. Also, extreme events are generally of great interest to society, so you could think of these forcings as forms of extremes. They're not extreme events in the sense of not being brief or, you know, rare from a statistical standpoint. But there are actually such brief extreme events in the paleoclimate record. So if you want a long record of tropical cyclones, for instance, if you want to know the statistics of tropical cyclones, well, as you well know, 50 years of 50 years of aircraft observations are not really enough. But if we could have a long record of, let's say, 10,000 years, we could characterize these return intervals a lot better. Other things like volcanic eruptions, which I'll touch on, are examples of extreme events for the Earth system. They are the closest thing that we have to a delta function forcing, and that gives a major kick to the climate system and under which we can appraise its response. And again, we have a handful, maybe 2 or 3 well-observed volcanic eruptions in the historical record. You know, the most recent being Mount Pinatubo in 1991. But by geologic standard, it's actually a puny eruption. And so if you want to know the response of the system to a really big change, like the Samalas eruption of 1258, then you have to look into the past. But from a statistical perspective, I would argue that the main reason we need paleo is that we need more degrees of freedom. That the true extent of climate variability over the 20th century is undersampled. And if you want to really fully characterize the range that the system is capable of, or even the simple statistics like the spectrum of variability, you really need to have to look at paleo. And from a point of view of model testing, the paleo record offers a true out-of-sample test for climate models. It offers a way to verify that their physics works well for cases in which they weren't trained. So if you think, for example, about convective parameterizations, they're usually carefully tuned to reproduce aspects of the present. What happens if you take them on a wild ride in a vastly colder or warmer climate? That's one of the things paleo can shed light on. All right, so I'll be talking about two main things. One project that I'm very fortunate to be part of called the Last Millennium Reanalysis that's been funded by NOAA. We actually had our last project report last September in this very room. And that's a project that was led at University of Washington by Greg Hakim, Eric Steig, and I also want to acknowledge collaborators Dave Anderson and David Noon. I'll also be talking about one of the aspects of my work that has arguably made this possible, which is Paleoclimate Informatics, which is really working on the data side, cleaning up the data on a massive scale so that they can be ingested by learning algorithms. And then I want to acknowledge my main co-conspirators, Nick McKay at Northern Arizona University, with whom I've done work on almost all of these things, and my postdoc, Deborah Kidder, as well as various students and other collaborators, including Kevin Chukaitis. Okay, so I just told you that we need paleo to test climate models, but that's all well and good. But if you think about climate models, actually, I prefer to call them climate simulators, because it's really three things. If you want to simulate climate, you have the model itself, but you need to feed it the appropriate boundary conditions and initial conditions. You can have the best model in the world. If you don't initialize it properly, you're toast. At least for something like decadal hindcast. You could argue that, a century into the future, the system has forgotten the initial conditions. But I'll actually challenge that later. Be that as it may, the output of these models is something that's firmly couched in the language of physics. You have things like temperature, precipitation, pressure, vorticity, the wind field. That's physics. But that's not what we measure. If you go into paleoclimate records, you often measure the ratio of stable water isotopes, like oxygen 18 or deuterium. If you look at trees, sometimes you measure simple geometric quantities like the ring width accrued by a particular tree over a growing season. In fact, in the past workshop here, we've cored a tree right here outside NCAR. It probably still bears a mark. So basically, this is all couched in the language of chemistry for the most part, either organic or inorganic chemistry. And as you know, physicists and chemists don't get along very well. So there's a fundamental language barrier between the two things. We'd really like to use these observations to constrain climate models, but there's a fundamental incompatibility here. Now, what we would really need to do is erase that language barrier, and we have two ways to do that. We can either do it the inverse way, or we can do it the forward way. And the inverse approach is what's been done for a long time. I would argue that it's a fundamentally fraught approach because basically there's a many-to-one mapping between the climate state and what you might observe in the proxy record. So in other words, it's not an invertible function, not easily anyway. But you can apply a forward approach, and using the tools of either Bayesian inference, basically Bayes' theorem, or data assimilation, which can also be understood from a Bayesian perspective, you can actually constrain the model state from these very indirect and noisy observations. I insist upon the fact that they're noisy. So obviously, for those of you who aren't used to dealing with nice data sets, there's a little note of caution here. You can't really go in and apply your plain vanilla algorithms to paleoclimate data, because not only are they noisy on the y-axis, so what you would traditionally call the dependent variable, but they're also noisy on the x-axis. Sometimes the timing of the perturbations is not precisely known, and that's definitely something that I've looked long and hard in the time series literature, and usually the one thing that you know is the time, right? So you have to deal with fundamentally new tools. Now the speech processing literature actually has some tools for that, which should be used. If you guys know anything about that, I'll be happy to discuss that with you. All right, so let me tell you a little bit about the last millennium reanalysis. Hopefully there'll be a little something for everyone here, including for the few of you who actually are climate scientists. Now this year, 1998, marks the anniversary of a very famous curve, the so-called hockey stick. How many of you have heard or seen that curve before? Okay, so that's a very noted one. So it was published in a paper by Michael Mann, Bradley, and Hughes in 1998, and the follow-on in 1999. And in this paper, they concluded that known hemisphere mean annual temperatures for 3 of the past 8 years, so for basically the 1990s, are warmer than any other year since at least a millennium. So that's a very powerful statement that global warming, as we've seen it, seems unprecedented in 1,000 years. And basically, this is the reason why this was called a hockey stick. It looked like there was a long-term cooling trend with obviously quite a few wiggles along the way, but that there had been an abrupt warming starting in the 1850s, more or less coincident with the Industrial Revolution. Now, this became very widely used in climate circles. It figured prominently in the third IPCC report, but it also triggered a whole lot of resistance and criticisms, some of which I would argue were well-founded. In particular, the statistics used in that were fairly rudimentary, and there also weren't a whole lot of data going into this. And so some people were very quick to latch onto this result, which by all accounts should be carefully investigated. In fact, there were no fewer than 2 congressional inquiries, a rogue one led by Edward Wegman, a statistician, which remarkably there was not a single climate scientist in that panel, and then a proper one led by a proper panel of experts from the National Academy of Sciences, which had a mix of statisticians and climate scientists. I don't need to tell you that they came to different conclusions. So anyway, that was sort of the state of the art in 1999. There was these very patchy reconstructions of surface temperature in various times in the past. So here you have 1791 on this graph, 1816, the so-called year without a summer on this one, which incidentally was the year after volcanic eruption, where you see large-scale cooling over the mid-latitudes, in particular North America, and that is why this was called the year without a summer. But it's very noisy. First of all, it's very coarse resolution. There's lots of gaps, and also the uncertainty quantification wasn't terribly good. And so over the past 20 years, there has been a lot of effort by my community to try and improve on this, and improve on several fronts. Improve the stats, methodology, and improve the data that went into the study. So on the data front, I was just having a conversation on the bus with Gustav this morning, who said that they were able to give this database to a master's student, which is a wonderful news, because we put a lot of time into cleaning the data to the point that you could use it for a 2-month internship. A decade ago, assembling a database like this would have taken probably a decade of your time. Certainly, this was the work of about 100 scientists. I think we have 98 co-authors on the paper over the course of more than 5 years. And that's not counting the data generation. It was just assembling the data from the published record and cleaning it up, putting it into a standardized fashion that could be ingested by some kind of statistical learning algorithm. And so the only point I'll make here is that there's close to 700 records, that they are very diverse. You have some from trees, you have some from corals, you have some from ice cores. They have very different resolutions. The vast majority in this database are annual, so you have one data point every year. In many cases with the corals, you actually have monthly resolution, which is great, but there's plenty of other records, in particular the marine sediments, where you have an average resolution on the order of a few decades. So you're dealing with a very different information content between these different records. That's something that a good learning method needs to take into account. Also, as you can see here, the number of proxies as a function of time decreases rather sharply. So there's not many trees in the first millennium. The corals all but vanished before 1600 or so. And in the first millennium, there's a fairly even mix of ice cores, lake cores, marine cores, and trees. So again, this is a headache for a machine learning approach because you have to deal with missing data, you have to deal with the changing composition of predictors effectively as you go back in time. But be that as it may, at least it's usable and ingestible by a computer, which is a very big improvement over the past. So one thing we wanted to do is apply a different and a more comprehensive way of learning about this data set. And the way to do that for us was data assimilation. Oh yeah, before I go on, we often talk about big data, and certainly when you're talking about terabytes of satellite data, you're in the realm of big data. All of this data here, these 700 data sets, fit on a thumb drive. In fact, it's just a few megabytes. So it's not big data in terms of volume, but I would argue it's broad data. It's messy, it's global, it covers a big time span, but it's not big in terms of volume. Nevertheless, it gives unique challenges to some kind of informatics approach. All right, so the framework that Greg Haykim championed is using basically the same approach as is used in weather data assimilation, although in that case it's offline. We use offline assimilation because the predictive skill that you get from one year to the next is not terribly great. Of course, you have a lot of predictive skill from one day to the next in weather prediction, so there's a lot of reasons to do some kind of forward-looking projection. But basically, we use climate models in this context not to propagate the state forward, but basically to give us an ensemble of climate states. So we use long integrations of climate models to characterize the state in terms of the physics or the thermodynamics. So basically any variable that's output by your climate model, including NCAR's homegrown CESM, which is one of the models we use. And we use fields from the atmosphere, from the ocean. Notably, we make use of water isotopes, which is one of the quantities that's now being tracked by such models. Was not the case until relatively recently. And we use that as basically a large statistical ensembles of climate states from which we pull random draws. And then what we do is that we run these through proxy system models. That is to say, it's a forward operator that basically simulates what an ice core, coral, or a tree would see if they lived in the world of this climate model. And from that, you get a forward estimate, which is your H hat, and then from that you derive with the so-called innovation, so the difference between the actual observations, Y, and your forward modeled observation, H hat, and that enters the Kalman filter equations, which are probably familiar to many of you. And so basically there's a cyclical approach here, and well, that's basically the general gist of it. Now, this approach was very attractive to us because in the many efforts that had been made to improve upon the methodology of Mann et al., there had been attempts to use, for example, Bayesian hierarchical models, which are certainly very powerful and can provide a very complete quantification of errors. But one issue that we always had is if you think about a tree, for example, it doesn't just care about temperature, it also cares about moisture. And so if you have to give it a prior on these two fields, temperature and moisture, you also have to take into account the covariance between these two fields. And coming up with priors that that represent a geophysically realistic covariance between these fields is just very difficult to do. A much simpler way to do it, and this is basically what we use as our prior, is the climate state from a numerical model. So at least it obeys physical principles. It doesn't violate them from the outset. And that's a big improvement, arguably. Now, there are problems, of course, because these climate models are not perfect. So the spatial covariances that you have are not the ones that you would observe exactly in the real world. So they're an approximation. But there's various corrections, bias corrections that you could make. So basically, we use the climate models to inform about relationships over space. But because of the way we pull the random draws, if you got no information at all from the proxies, your reconstruction would be completely flat. Okay, you get a flat line, maybe actually an ensemble of flat lines, so you get something with a distribution that is isomorphic to the one of the model, but you get absolutely no variability. All of the variability comes from the proxies. So the proxies really give you the timing of the fluctuations. And so in the curves that I'm going to show you later, every single wiggle up and down is driven by the proxies. It's not driven by the climate model. And then the amplitude itself, the amplitude of these wiggles comes from the proxy system models. Now, a lot of what I've done the past few years is to develop physically based models for these. It turns out that we're not quite at the point where we can use them in this assimilation framework. So we're going to use, in fact, very simple linear regression models. So basically, we model the proxy as a linear combination of temperature and moisture. And well, one of the nice things compared to other approaches is that because we use a forward estimate, we can actually incorporate things like the seasonal dependence. For instance, trees lay down only one growth ring per year when it's not a terrible year. But they only grow really during summer. So the part of the temperature field that they're sensitive on corresponds to, roughly speaking, and it depends on location, but mostly May and August. And so we're able to take that into account using a forward model, even a simple statistical one, but you would never be able to do that with an inverse approach. So that's one of the benefits of using this framework, is we can incorporate things that we know about the system. We don't have to pretend that annual temperature is a linear combination or is linearly related to annual growth rate. When in fact we know that this doesn't respond to annual temperature, it responds to summertime temperature and moisture. Okay, so the beauty of this framework is that it allows you to put in some theory, or at least some of the knowledge that you have. It's not an unsupervised learning approach where you don't necessarily inject any information here. Because there's so little data to play with, you can't afford the luxury of not injecting what you know. Okay? And so what we know is that climate obeys the laws of physics. So there's a relationship between fields like temperature, pressure, and wind field. They obey large-scale dynamical balances that you can't violate. And similarly, corals grow in the tropics. They don't grow at the poles. Vice versa for ice cores. Actually, there are ice cores in the tropics, just very high elevation. And trees have certain biological imperatives, and they're not just temperature plus noise, as we've represented them for some time. Okay, so I'm going to skip over that. Basically, in the latest iteration of the LMR, we have 3 data sources. The main one is this Pages 2K database I was telling you about, but we actually have vastly expanded it with thousands of more trees. It's not terribly important for what I'm going to show you. Now I want to move on to some results. So for this particular thing, we have 3 ingredients. Oops, sorry. We have the proxy data, which are here on top. We have the data assimilation framework. And we have some kind of calibration. At this point, we still need some calibration of the proxy system models. And so we use instrumental data sets like ATCRU-T4 or precipitation data sets like GPCP. And from that, you obtain an estimate of temperature. And the first thing you want to do is validate it. So the LMR estimate here is in black of the 20th century. I think it's a 95%. You might interpret it as a credible interval. Basically, it's the central 95% quantiles of the ensemble distribution. So one of the nice things about this is that because we pull random draws from this, we obtain an ensemble of reconstruction. So we don't have just one, we have a full ensemble. Actually about 20,000 members. So that allows you to do some fairly nice stats, if that's what you're into. And what you can see is that this estimate, and again, I want to emphasize that every single wiggle here, every single up and down is driven by the proxies. Now, the overall amplitude, and the reason why the amplitude matches that of the observations is that it was ostensibly calibrated to that. But that's the only place where the instrumental data come in. It's only about giving you the amplitude and basically the right starting point and ending point. All of the wiggles here are coming from the proxies. And it's absolutely staggering that we actually get a closer match to instrumental data than, for example, the 20th century reanalysis. Don't tell that to Gil Campo, he doesn't like to hear that. Of course, we have spatial fields, so we can do the validation over space. And this is the so-called CE statistic, the coefficient of efficiency, basically a scaled version of the mean squared error. So 1 means perfect reconstruction, 0 means, and below means useless reconstruction. And you see that over much of the globe, we are solidly in the positive. There's, of course, problem areas around the poles, where basically we have very little data to begin with, so it's not entirely clear whether we can meaningfully validate over there, apart from perhaps the last 20 or 30 years. So we found this to be very encouraging. We've showed steady gains since we started doing this in 2015 and 2016. Basically injecting more data, injecting more information in the forward models has led to steady gains in the quality of the reconstructions. So let's do a little bit of science if we have time. So one of the things you might want to do is look, for example, at the evolution of temperature over the past 2 millennia. And in red here, you have our reconstruction of northern hemisphere temperature. In purple, you have southern hemisphere temperature. You can see a lot more variability in the north than the south. Partially, this is to be expected. There's a lot more land in the north than the southern hemisphere. So the amplitude of climate fluctuations tends to be a lot higher in the north. But it's also a reflection of the fact that we have very poor coverage in the southern hemisphere. So we have relatively flat reconstructions there. Now, overlaid, these vertical lines overlaid on this graph corresponds to volcanic events that are represented here from a reconstruction of aerosol optical depth, basically a measure of how many aerosols there are in the atmosphere and how effectively they scatter incoming solar radiation. And the 40 largest ones are marked here by this red triangle, and they are the ones that are marked here. And you can see that in many cases, you see sharp drops in temperature coincident with volcanic eruptions, which is, of course, exactly what you'd expect. We know with the instrumental record that's what happens. It's just very nice to know that you have two completely independent data sets, one in which you reconstruct the temperature basically from trees and corals and ice cores, and this one where this is only based on ice cores, but it doesn't know anything about temperature. It just knows about the amount of sulfate aerosols captured in the ice core, and from that you reconstruct the magnitude of the eruption, and you get at least a nice coincidence between these events. So now you may ask other questions. You could say, does the magnitude of the temperature change scale with the magnitude or the reconstructed magnitude of the aerosol optical depth? You can also, since we have a multivariate reconstruction, you can look at changes in temperature, which are the Does this work? Okay, I'll do this, but the think it's going to screw up the recording. No, that works? Okay. So basically you can now, for the first time, really look into this in a multivariate way. I'm not going to get too into the details. If you're interested, we can talk later. But basically for various eruptions, we now have representations of the dynamic state of the atmosphere and the ocean for a lot of fields of climatic interest. And that allows you to do some interesting things, like, for example, testing climate models. So here this is a figure from the last IPCC report, which showed that there was a discrepancy between the response of the models to volcanic eruptions over the past millennium, so using the so-called PMIP3 simulations. And you see usually a very sharp drop in temperature following an eruption. So here they've all been lined up to year 0. You basically line up, I think there's 20 or 25 eruptions in there, the largest of the past millennium. And you see that there's a sharp drop in temperature the year after the eruption, and then there's a relatively sharp recovery and going back to normal. Now, if you look at the reconstructions, they displayed a more muted pattern, and one in which the recovery took a lot longer. So that was puzzling, but there's all kinds of reasons why maybe you could distrust these reconstructions. But now we've done this again with LMR, we've done this with different reconstructions based only on tree rings. This is the work of Kevin and Chukaitis with the NCAR consortium. And you see that actually this pattern of a very extended recovery persists. So we just got funded to look more deeply into this, but if it's true, it tells us that there's something about the physics of climate models that's not quite right, that they recover too quickly from these eruptions. And if these reconstructions are right, then in fact they should, the climate cooling following eruptions should be persisting. So from that we actually learn a lot of dynamical information, and we're able to test the physics of the models. Perhaps it's something having to do with ocean dynamics, perhaps it has to do with parameterizations of deep convection in the ocean. So there's a lot of questions there. Another thing that I've been having fun with is revisiting the hockey stick. So basically this is the reconstructed temperature again with the IQR, the interquartile range in deep blue, and with the 95% highest density region in light blue. And you can see this is something I've been looking for in a statistical method for some time, that you would expect the error bounds to widen back in time because you have fewer and fewer observations. Nevertheless, if you look at many estimates in the literature, these error bars do not change over time, which is obviously not something you want. So, without having designed it this way, that's one of the nice outcomes of the last millennium reanalysis, is that it really does give you this. Basically, you regress back to the prior in the very early times of reconstruction, so it's very flat. I wouldn't trust this particular time evolution. All it tells you is that, well, the real evolution could be any time within that, and as you get back closer to the present, you have tighter and tighter bounds on it. But nevertheless, you can ask questions such as, how unusual is the recent mean temperature or the recent trend? And I've done this for intervals of, let's say, 10, 25, 50, or 100 years. So you could ask, how unusual was the last decade or the last 5 decades? And you can do this and compute the probability that the most recent time is unusual. So basically the difference in the means is positive. And you can see that with very high confidence, except perhaps for 100-year means, we get that the vast majority of ensemble members here are above the rest of the ensemble members. And you can play the same game for the trend. And here you get a slightly different answer, that the 100-year trend is the one that is the most unusual. And it's the 10-year trends that are not necessarily so. Again, it's not completely unexpected, because we know we've had these abrupt events in the past, like volcanic eruptions, and then when the system recovers from these eruptions, there's a very abrupt increase in temperature. So on decadal scales, perhaps the rate of the last couple of decades wasn't very unusual, but definitely if you look at a 25 or 100-year time scale, it looks very unusual. And you can also do this over space. So this is the probability that the last 30 years are anomalous in the context of the past 2,000 years. And yellow here means close to 100%. And you can see that for much of the globe, we are, in this range. And the regions where we are not, are typically in these very undersampled regions of the southern hemisphere. So it could just be data coverage bias. Okay, before I have to leave the mic, let me get to the second part of my talk. So what did it take to really do this? It obviously took some data assimilation, took some climate models, but it took a lot of well-formatted data. So if you look at the ingredients of paleoclimatology, basically all of these things are relatively under control. You have very qualified people who work on these aspects of data collection, data analysis, and you have people like yourselves who do the statistics, the computer science, the processing. But there was a crucially missing part, which is basically once people publish their records, they would, and I kid you not, they would email them to each other or to NOAA as a spreadsheet, and that was pretty much it. And so they were all in completely disparate formats, meaning that you'd have to write a different piece of code for every single data set. They all called things differently. It's basically a nightmare from a coding perspective. So it required a lot of patience, and it wasted hundreds or thousands of hours of people time. There's entire PhD theses that have been wasted on this, while people could have actually been doing science. Instead, they were doing data cleaning. So we thought that we could perhaps improve on this state of affairs, and using a grant from EarthCube, from the National Science Foundation, we created this thing called Linked Earth. So this is joint work with Julien Emile-Geay at the Information Sciences Institute. She was a speaker here a couple of years ago, and Nick McKay at Northern Arizona University. Now, I don't have a ton of leisure to get into that, but all I'll say is that this is a data platform that looks like a wiki. So basically, it's something that where the community can log in and edit data sets like they would edit a normal wiki page. They can have discussions. They can participate in deciding about data standards. They can vote. And this is how we represent, for example, the data compilation, like the Pages 2K one I was telling you about. Now, there's actually quite a lot of cool informatics that goes into this, because the guts of this are a semantic wiki. So it uses semantic web technologies under the hood. This is completely transparent to the user. So our paleoclimatology friends who never want to hear the word triplet or JSON in their life don't have to do that. They only have to learn the word wiki. And if they've ever edited a Wikipedia page, they basically know enough to do this. And that enables a lot of cool things. So I'll show you some of that. Now, what's really underneath it all is that to be able to make this work, we had to create an ontology. So we had to really represent the data at a very deep level in an extremely structured fashion. And it took us an inordinate amount of time to really do this in a logically consistent way. But we believe that we have something that makes sense now. So now we have at least a standardized way of calling everything. We have a standardized nomenclature, and we have pieces that fit together so that they're highly structured. And so an algorithm could take advantage of them. Underneath it all, if you peel another layer, there is a standard format that Nick McKay and myself created called Lipid. And basically all it is a bunch of tables in CSV that are wrapped together with metadata in the form of JSON LD. LD is for linked data. So one of the things that's nice about this is that we've used the schema.org framework. And so that means that those data, when they're published on the wiki, are immediately accessible to search engines. You probably have heard, in fact, I saw that on the Climate Informatics blog a few weeks ago, that Google started a structured data testing tool. Well, not testing tool, but structured data searches. Well, one of their first things for paleo, basically all the data that we have in a database that are properly described from Google's point of view are in there. Right now it's just 2 because they insisted on a description field, which is basically a verbal description of data set. So we don't have that yet, but that's an easy fix. We just have to convince our colleagues to describe their data sets. So that makes those data instantly discoverable, and because they're so structured, they're very usable. Now, in the process of doing this, we realized that I don't need to tell you about the importance of data standards or standards in general, right? If we didn't have standards for, let's say, power distribution, then my laptop and your laptop would have to use different power distribution sources. Modern life would not exist. And same thing for data. Now, we realize that a data standard is really three things. You need a standard format in which you store the data. Most of you are probably familiar with NetCDF for most climate data. You can think of lipid, the linked paleo data format, as the NetCDF of paleo. But as you probably know also, for a long time people were calling fields with different names within NetCDF files. So it's not enough to just have a coherent format, you need to have coherent conventions. And so now with this ontology we have a coherent terminology, and we're also evolving, this is work in progress by my former postdoc Deborah, we managed to elicit from the community that they vote on standard practices, that they decide what information should be archived in what case. So we're now evolving to the point where more and more paleoclimate datasets are going to be standardized, and that is to say amenable to a treatment by people such as yourselves, where you're not going to have to worry about all of this, you can just take it and use it. And so basically lipid enables to now export all of this data to various entities and interact with other data sources. But the most important aspect of it is that now you can start doing some fun data science with it. So in the last few minutes, let me talk a little bit about the next steps and what it would do to enable more paleo data science. So we have an ontology, and as it turns out, an ontology, if it's well done, really describes logical relationships between objects. And so that means that you could do things such as formal reasoning or inference. You could carry out extremely complex queries. You could even have AI systems that do quality control in the background and sort of flag potentially problematic or conflicting data sets without people having to do that manual labor. And it also means that you could design intelligent workflows, where you could design scientific workflows that take into account the rich metadata that is embedded in these data sets. So basically, the day is not so far where you could ask an AI to do a lot of the tasks that are now manual and very labor intensive. You can also start actually doing science with it more. So this is an example of work done by my student, Feng Zhu. And what you see here is he's done some spectral analysis of all the records in the database. Again, this is using the Pages 2K database. So there's about 700 records. And he's using a fairly elaborate spectral technique called a weighted wavelet Z transform. It's basically wavelets that account for missing data. And again, a few years ago, this would have taken a few years. But this only took about a week, because once you have properly structured data and code, then you can do a lot of cool work. And one of the things that we've done with this is characterize what's called the continuum of climate variability, and you can use that. This red curve here, this is actually from LMR. You can use that to evaluate the spectrum of variability in climate models, and you can start again doing some forms of model evaluation. Now, here are a few areas where I see climate informatics and this community contributing more to this problem. What I brushed under the rug is that in this Kalman filter, of course, there's quite a bit of stats that lurks, including some non-trivial covariance estimation. There's a nice role to play for spatial statistics in better carrying this out. There's also a role to play for example, downscaling, because here we have fairly coarse resolution models, and we ask them to predict conditions at a single site. And for example, trees that live on this side of the foothills experience a different climate than trees on the other side of the foothills. That's not something that can be represented by a coarse resolution GCM, but with proper downscaling techniques, you might be able to do that. Also, by design, we decided to try to see how far we would go by just using paleo observations in the assimilation cycle. But you could also use modern observations or early modern observations, like oldweather.org has these old ship logs, these very old pressure observations from the early 19th century. you could imagine incorporating that as well, and basically using all data sources, not just the proxies. And basically there's a lot of applications to this, because now you have a multivariate climate field over the last 2,000 years with error estimates, and you can use it to validate models. You can use it to do some kind of machine learning for whatever you're interested in. And I would argue where I would want to go with this is better initializing decadal forecasts, better testing decadal hindcasts, and therefore better initializing decadal forecasts. All right, I don't really have the time to go to this, so I'll switch to the conclusions and I'll take a few questions. So I hope to have convinced you that the future is now and that we can have a future without taking a look at the past. Thank you.